All right, gentlemen, let's continue. So, another quick example using the Gaussian elimination method to solve the system. Let's use Gaussian elimination and solve this system. Let's change our marker color to green. Okay, first we need to write the augmented matrix, as you know, right? So just keep the screen on. All right. So our augmented matrix here is W, X, Y, Z. These are the variables unknowns. So here we have 1, -1, -1, and 2. And here we have 1. Right? And the second row, 2, -2, 2, -2, -1, and 3, it is 3. Now here we have W is -1, X, it is 1, Y, -1, Z doesn't appear, so it is 0, and the constant term, it is -3. Right? So that's the first step. We have to write the augmented matrix. In the second step, we need to reduce this to row echelon form. And to do this one, let's say 1, -1, -1, and the 2, 1. Let's just multiply the first column, right, by -2 and add it to the second row. What do we have here? -2 times 1, -2 plus 2. So here we have 0. -2 times -1 is 2, plus -2 is equal to 0. And -2 times -1, it is 2, plus -1 is equal to 1. And here we have -4 plus 3, it is -1. -2 plus 3 is equal to 1. And how about here for the third row? We need to just add the first row to the third row, right? 1 plus -1, here we have 0. And -1 plus 1 is equal to 0. -1 plus -1, it is equal to -2. 2 plus 0, that's equal to 2. 1 plus -3 is equal to -2. And you see here, the third row is just a multiple of the second row, right? 2, 2, 2, right? If you just multiply the second row by 2, actually not 2, by -2, we will get the third row. -2, -2 times 1, -2. -2 times -1 is 2. So it is -2 times 1. So if you just multiply by 2 and add it to the third row, what we have here? 1, -1, -1, 2, 1. So here we have 0, 0, 1, -1, 1. So here we have 0, 0, 2 plus -2, 0, -2 plus 2, 0, 2 plus -2, it is 0. All right, so I don't need this. Let me just erase this. In the next step, if actually we just write the corresponding system, right, to this augmented matrix, what we got here? We got here W minus X minus Y plus 2Z, that's equal to 1, right? 1 minus 1 minus 1 plus 2 equals 1. And next row is W, 0, X, 0. Here we have Y. Here we have Y, and the minus Z is equal to what we have here. It is 1, right? And the third row, all are 0, so we don't have to write anything. As see here, we have 2 equations here and 4 variables here. And how do you solve this equation? And actually, that means that this system has infinitely many solutions. Why? Because here we have 2 equations and 4 variables. Usually, if the number of variables is more than the number of equations, that system has infinitely many solutions. So there's more than one way to assign parameters, but we will proceed to use back substitution, writing the variables corresponding to the leading entries, the leading variables, right? In terms of the other variables. And those variables are called free variables. Okay, so in this case, the leading variables are W and Y. Why? Because as you see here, in the first equation, right here we have W. That is a leading entry. And how about here in the second row, right? That is a leading entry. This is a leading entry, that's a leading entry. So here leading variable is y. And others are, what is it? Free variables. So if I just introduce, let's say here we have z as t. Okay, what we have here then? Here take to the side, then y will be equal to 1 plus t. And also here we have, okay, w, y, these are leading variables and others are free variables. And here we have z, free variable, and also x is a free variable. And also let's say here, x, what is it? Is, let's say s. What is t? Any real number. S, any real number. But this y is dependent on t here, right? Then here we can write w. What is w? 1 plus x, which is equal to s, plus y, that's equal to 1 plus t, minus 2z, that's equal to 2t. Or if you just simplify this, here we have, what is it? Here we have 1 plus 1, that's equal to 2. And here we have s, right? And plus s, and t minus 2t, that's equal to minus t. Okay. So now if we assign, after assigning parameters, now we are going to write the solution in vector form. How can you write this? Here we have t, 1 plus t, s, right? And here we have the thing. So if the solution is this w, x, y, and z, right? And what is w? W is this. It is 2 plus s minus t. And how about x? That is s. How about y? 1 plus t. And how about z? That's equal to t. Now, actually, I can just write it as, here we have constant vector, that is 2. And here we have nothing, that's just 0. And here we have 1. Here we have nothing, so we have 0 here. Plus, now if I just take this s out, right, because it's just any real number, scalar, so I can just keep this out. So here we have, what is the coefficient of s? That's equal to 1. Coefficient of s, that's equal to 1. Coefficient of s, no s, that means it is 0. And also here we have 0. Plus, and t, and here we have the coefficient of t, negative 1. Here we have 0. The coefficient of t, it is 1. And here it is 1. Right? And that is the first vector, and second vector, and third vector. And if you remember, what does it represent? Actually, it represents a plane, right? It represents a plane. Of course, actually hyperplane, because here that is in 4-dimensional space. All right. Now we have another, what is it? Keyword, rank of a matrix. Did we actually write this rank there? Did I see that? Let me just go and reading free variables, rank of a matrix. Okay, we are talking about this rank of a matrix. Good, it's there. Now we are going to see this rank more frequently from now on. Let's just see the definition here. And after that, we will just see how we use and what information does it give us. And why is it important? You understand its importance as they actually practice more and more problems and see the use of this word in problems. So the rank of the matrix here is defined as the number of non-zero rows, and it is row echelon form. So if you're given a matrix, first bring this into, or reduce it into, it is row echelon form, and after that count how many non-zero rows does the matrix have. So that gives actually us the rank of the matrix, and later we will see that it gives some information about the matrix. So that much is enough for now. And immediately we have a rank theorem, the first part here. Let A be the coefficient matrix of a system of linear equations with n variables. Okay, so we're not talking about the augmented matrix. Here we are talking about the coefficient matrix, right? Only the matrix that consists of all the coefficients of the system. So if the system is consistent, and as you remember what we mean by consistent, either it has a unique solution or it has infinitely many solutions, right? So if it is consistent, so we are not talking about the third case that the system has no solution. We are not considering that in this case. Either it has one solution or infinitely many solutions. Then number of free variables. Number of free variables is equal to n minus rank of A. Okay? And immediately if you just move back to the previous question, for example, what is number of free variables here? How many free variables we have here? As see here, we have this t, the first free variable, and s, we have the second free variable, right? And as see here, how many variables, I mean unknowns we have here? Here we have 1, 2, 3, 4, except for the augmented column, right? Actually, we are talking about only the coefficient matrix. It has 4 columns. That means that we have 4 variables. So number of free variables, let's say that's equal to n. And what is n? N is here n variables. Here we have 4 variables, w, x, y, z. So that is 4 minus, and it says that the rank of A. So here, how many non-zero rows we have here? That is 2, right? Because the last one is 0 row. So it is 2. So that's equal to 2. Actually, it is consistent with this example, right? So here we have 2, right? 2 free variables. That's equal to the number of variables minus the rank of the matrix. That is what this theorem says. Okay. Example 7. And how about this example? If you look at this example, let's say we are given a system of linear equations. Here we have 3 equations. It is augmented matrix is this. And how about the coefficient matrix? Okay, reduced echelon form of this matrix is this. And as you see here, this part is the coefficient matrix. That means that this system has 3 variables. Now, how many free variables we'll have when we solve this one? So as see here, we have any non-zero row here, right? So n is a number of variables. Here we have 3 variables minus what is the rank of this matrix? It is 3, because the rank of A means the number of non-zero entries in the row echelon form of the matrix. So that means if we solve this, we will have no free variables. All will be leading variables. That means that x will have a constant number, y, and the z it will have exact numbers. They will not be dependent on any other parameter. Another example, how about this one? As you here, we have a system of equations. We have 3 equations and we have 4 variables, right? That is w, x, y, and z. So if you just write the augmented matrix, here we have 1, -1, -1, 2. That's the first line and the second line and the third line, right? And if you just reduce this to row echelon form, we know how to do that. We already did a few examples. And here we get this reduced row echelon form of this matrix. As see here, the last row is a 0 row, right? So how many non-zero rows we have? Here we have 2. So that means that if I just denote this coefficient matrix, okay, this one as A, then the rank of A here is equal to 2. And how many actually we have variables we have, excluding this augmented line, right? We have 1, 2, 3, 4. So we have 4 variables. Then the number of free variables will be, when we solve this system, 4 minus 2, we will have 2 free variables. So number of free variables, that's n minus rank of A, that's equal to 4 minus 2, which is equal to 2. That is in the example 4, just using rank. I'm just giving this example so that you get more familiar with, the rank and also with its pronunciation. Okay. All right. Gauss-Jordan elimination. Guys, so far we have been talking about Gaussian elimination, right? And also we use that methods. As you remember, Gaussian elimination method means if you're given a system of linear equations, we need to write the augmented matrix. And second, we need to reduce this to row echelon form. And after that, using back substitution method, we need to solve the equivalent system, right? But here we will have a little bit more powerful methods, that is Gauss-Jordan elimination. Maybe these people together, they published a paper on this, or they work on this together, or maybe independently. Actually, they discovered this method. That's why it is credited to their name, Gauss-Jordan elimination. Okay, Gauss is also one famous mathematician from Germany. Anyway, so here, what is the difference? Now here we're using row echelon form. Now we are adding one more word, right? That is reduce. Actually, it is more simplified form. It will be in a more simplified form. So a matrix is in reduced row echelon form if it satisfies the following properties. Number one is it is in row echelon form. Okay, we know what we mean by this now. So the leading entry in each non-zero row is a 1. So now we are adding one more condition, right? In the previous example, if you remember, the leading entry could be 1 or 2 or negative anything, but also we are making 1. Well, how? If the leading entry is A, just multiply that row by 1 over A, and we will turn it into 1. So another condition is for a matrix to be in reduced row echelon form, that is RREF, and also a lot of in softwares like MATLAB, for example, if you just write RREF and write here matrix, it evaluates the reduced row echelon form of the matrix. So the leading entry in each non-zero row is 1, and each column containing a leading 1 has zeros everywhere else. Now in row echelon form, if you remember, only under 1, right? It must be 0. All entries under leading variable, it must be 0. But here, number 1, that leading entry must be 1, and above this one and below this one, all entries must be 0. Then we call that the matrix is in reduced row echelon form. Examples. The following are all the possible reduced row echelon form of 2 by 2 and 3 by 3 matrices. Let's say we are given 2 by 2 matrix whose elements are something. So either it can be in this form, as you see here, these two things are leading variables, right? So that is 1, also that is 1. And everywhere else it is 0. Everywhere else it is 0. And also here we may have this. Here we have only one leading entry, and under and above there's nothing, it is 0. And here it may be A, because I cannot how to say element of this A, because here we have only zeros. Or also we may have in this form, so here leading variable, everywhere else it is 0. And also here we have 0, 0, 0. It's already in reduced row echelon form. And how about for 3 by 3 matrix? Either it may be in the first form, that is actually the best form, and or 1, 1, and all are 0 in the third row. So that is leading variable, everywhere else it is 0, leading variable, everywhere else it is 0, right? Or like this, 1, everywhere else it is 0, also the similar thing, and 1 AB, everywhere else it is 0, that is leading variable. Here, this one is leading variable, right? And here, there's a leading variable, and these are all possible RREF of 3 by 3 matrix. Okay. Use elementary row operations to reduce the following matrices to reduce row echelon form. All right. We have 1, 2, 3, 4, 6 examples. Guys, you may now have knowledge about these things, but if you want to do this fast and correctly, you need to practice the questions. And also I will send the message in Telegram, and the ones who are here, I think somebody sent his assignment to me. Guys, you should not send your assignments to me. You should send your assignments to Mr. Yi Hing. He is your assistant teacher, all right? He will grade your assignments, okay? So you need to send your assignments to Mr. Yi Hing, not to me. So let's get back to this question. By using elementary raw operations, we have to reduce the following matrices into RREF. So let's start from the first one. Okay, the first one, here we have 3, 2, 1, 4. The first elementary raw operation, let me just swap actually their rows or interchange their rows. Then we will have here 1, 4, 3, 2. And multiply the first row by -3 and add to the second row. It is 0, -3, -12 plus 2, that is -10. And multiply the second row by 1 over -10. We will have 1, 4, and 0, 1. It is in row echelon form, but still it's not in reduced row echelon form. So one more, multiply the second row by -4 and add it to the first row. Then we'll have here 1, 0, 0, 1. So that is reduced row echelon form of the given matrix. And it is too bright. Let me use purple. Second one, how about the second one? Here we have 3 and 5, 5, -2, 2, 4. Right? And first thing I have to do here is, okay, I will just interchange the first row with the third row. So we will have here 2, 4, here we have 5, -2, and 3, 5. Why actually do I do this? Because I can have 1 here easily, that's why. Now multiply the first row by 1 over 2, that is 1, 2, 5, -2, and 3, 5. And here we have 1, here we have 2. Multiplies by -5 and add to the second row. So here we have 0, -5, -10 plus -2, -12. And multiply the first row by -3 and add to the third row. So it is 0. So here we have -6 plus 5, -1. And one more, 1, 2. Multiply the second row by -1 over 12. That is 1. Multiply the third row by -1. So here we have 0, 1. Okay. Now multiply the second row by -2 and add to the first row. Here we have 1, 0, 0, 1. Multiply the second row by -1, adds to the third row. Here we have 0, 0. So now it is in reduced row echelon form. We cannot go further. That is in reduced form. Okay, that is what we mean by reduced row echelon form. How about number 3? Here we have 0, 0, 1, 0, 1, 1, 1, 1, 1. And interchange this. Here we will have 1, 1, 1. I just interchanged the first row and the third row. So here we have 0, 1, 1. Here we have 0, 0, 1. Right? And if I multiply the second row by -1 and add to the first row, we will have 1, 0, 0. And if you multiply the third row by -1 and add to the second row, we will have 0, 1, 0. And here we have 0, 0, 1. Now we cannot go further. That is the reduced row echelon form of this matrix. Okay. In a similar way, you can do these questions. Here we have 4, 5, 6. And let's do one more maybe. 4, for example. Here we have 2, -4, 2, -4, -2, 6, and 3, -6, 2, 6. Right? And see here in the first row, all numbers are divisible by 2. Let's multiply by 1 over 2. So here we have 1, -2, -1, and 3. And the second one, I have nothing to do, just leave it like this, or I can just divide by 3, right? So here we have 1, here we have negative 2, 2 over 3, and here we have 2. 1, negative 2, negative 1, and 3. Multiply the first row by negative 1 and add to the second row, so it is 0. So negative 1 times negative 2, it is 2 plus negative 2, that's equal to 0. Here we have negative 1, it is 1, 1 plus 2 over 3, that is 5 over 3. And here we have multiplied by negative 1, negative 3 plus 2, that is negative 1. Still, it's not in row echelon form, right? Because here it's not equal to 1, it's equal to 5 over 3. So let me multiply the second row by 3 over 5. Then here we have 1, negative 2, negative 1, 3. Here we have 0, 0, 1, minus 3 over 5. One more, since that is a pivot or leading entry, also leading entry, everywhere else in that column, it must be 0. So one more thing is needed here. I should multiply the second row by 1, just add the second row to the first row. Then we will have here 1, negative 2, here we have 0, 3 plus minus 2 over 5 is 15, it is 12. So here we have 12 over 5, and here we have 0, and here we have 1 minus 3 over 5. So now that is a leading variable. Everywhere else, entry everywhere else is 0. And also that's the second pivot or leading variable. Everywhere else it is 0 and they are 1. So that is the reduced row echelon form of this matrix. And 5 and 6 is practice for you. You can do it yourself. Okay, gentlemen, let's move on. Gauss-Jordan elimination. So what is the difference between Gaussian elimination? See here now we need to reduce the given matrix into reduced row echelon form. That's our augmented matrix. That's the only difference. And you'll see that by this method, the system, actually we will reach the solution of the system very quickly. So the first one, write the augmented matrix of the system of linear equations. 2, use elementary row operations to reduce the augmented matrix to reduced row echelon form, that is RREF. If the resultant system is consistent, solve for the leading variables in terms of any remaining free variables. That is the Gauss-Jordan methods. Solve the following systems by using Gauss-Jordan elimination methods. How many examples here we have? 4. Okay. Let's do the first one. All right. To solve A, first we need to write the augmented matrix. So here we have 1, 1, 1, 5, 1, 1, 1, 5. Second row is 2, 3, 5, 8. 2, 3, 5, 8. 4, here we have 4. Y, we don't have Y here, so it is 0. And coefficient of Z, that is 5. And here we have 2. That is the augmented matrix. So now we need to reduce this to RREF, right? Reduced row echelon form. So already we have 1 here. That's our first leading entry. Let me just write that row 1, 1, 1, 5. And multiply this by negative 2 and add it to the second row. So we are doing this negative 2 times R1 and adding this to the second row. So here we have 0, negative 2 plus 3, that is 1, negative 2 plus 5, that is 3, negative 10 plus 8, that is negative 2. And how about here? We should multiply the first row by negative 4 and add it to the third row. Negative 4 plus 4, that is 0. Negative 4 plus 0, that is negative 4. Negative 4 plus 5, that is 1. Negative 20 plus 2, negative 18. Okay. So, okay, now we have everywhere 0 here. Now, 1, 1, 1, 5, 0, 1, 3, negative 2, 0. Let's multiply the second row by 4 and add to the third row. So we'll have 0. 4 times 3, 12 plus 1, that is 13. 4 times negative 2, negative 8 plus negative 18, negative 26. And the last row is all numbers are divisible by 13. Let's divide them by 13. 1, 1, 1, 5, 0, 1, 3, negative 2. Here we have 0, 0, 1, negative 2. Okay, so now if I just add, multiply the third, okay. And one more time if I, all right, good. So now let me multiply the second row by negative 1 and add to the first row because I need to create 0 above this pivot, right? So here we have 1, negative 1 plus 1, it is 0, negative 3 plus 1, negative 2, and here we have 2 plus 5, that is 7. And here we have 0. And how about if I multiply the third row by negative 1 and add to the second row? Here we will have 1. So here we have negative 1 plus 3, that is 2. And here we have 2 plus negative 2. Here we have 0. And here we have 0, 0, 1, negative 2. Just simplify this. Okay, with this we are done, no problem. With this we are done, no problem. Now above this one, we need to create zeros, right? To do this one, I need to, okay, 1, 0, 0, it will not change. 0, 1, 0, it will not change. So first, I need to multiply the third row by negative 2 and add to the second row. So here we will have 0, right? And here we have negative 2 plus 2, 0. Negative 2 times negative 2 is 4 plus 0, it is 4. So here we have 4 minus 2. Now multiply the third row by 2 and add to the first row. So here we will have 0. And 2 times negative 2, negative 4 plus 7, that is 3. Now as you see here, that's the pivots, right? Leading entry, leading entry, leading entry. Now if you just write a system of this augmented matrix, what we have here? Here we have x. So here we have x on the right hand side, here we have 3. And here we have y, and here we have 4. And here we have z, and here we have negative 2. And which is just the solution of this system. All right. And B, let me just skip this. Let's do maybe the last question, D. And all right, then I think I will finish the class for today. How about D? D, first we need to write the augmented matrix. So we have 4 variables here, A, B, C, and D. In the first one, it is 1, 1. Coefficient of C, it is 2. We don't have D, so that's equal to 0. On the right-hand side, here we have 1. Second line, A, B, so it is 2, negative 1. We don't have C, so here it is 0. Coefficient of D, it is 1. On the right-hand side, we have negative 2. Third line, it is 1, negative 1, negative 1, negative 2. 1, negative 1, negative 1, negative 2, and here we have 4. Here we have A, B, C, D, 2, negative 1, 2, negative 1, 2, negative 1, 2, negative 1, and on the right-hand side, here we have 0. Okay. So it's a lot. What can we do? Immediately, let's just start with the easiest ones. Okay. So 1, 1, 2, 0, 1. Our pivot is already 1, so we don't have to change this. Multiply the first row and add it to the third row. Negative 1 plus 1, it is 0. Negative 1 plus negative 1, it is negative 2. And the -2 plus -1, -3 is nothing, so it is -2. It is -1 plus 4, it is 3. How about here, the second row, multiply by -1 and add to the third row. -1, 2, 2, it is 0. So the same, it is 0, it is 0, nothing changed here. It is 1 plus -1, it is 0. -2 plus 0, here we have -2. And just now, let me just write the second row. Second row, multiply the first row by -2 and adds to the second row. So here is 0. -2 plus -1, -3, and -6, -4 plus 0, -4. Here we have just 1, and -2 plus -2, that is -4. Right. And the last row, actually here, 2, -2, I can just write 1, -1 because they are 2. So here we have 1, -1, right? As see here, if I actually multiply this by 3 and add to the second row, right? 3 times -3, it will be 0. And -3 plus 3, it will be 0. Okay. So, all right. And after that, let me just interchange. All right. And here we have -2, -2. Let me rewrite this. All right. Here we have 1, 1, 2, 0, 1, 0. Multiply them by -1, 3, 4, -1. It is 4. Here, the third row multiplied by -1 over 2. So here we have 0, 1, 0, 1, 0. And here we have 0, 0, 1, 1, 0, -1. So this one is 1. Okay. Now, if I add the second row to the third row to the second row, what happens here? 1 plus 3, here we have 4, right? So here we have 4. And 1 plus -1, here we will have 0, right? Now, 4, 4, 4, if I just multiply by 1 over 4, we will have this. 1, 1, 2, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, and 0, 0, 1, 0, -1. Okay. All right. So, I can add the second row to the third row and multiply by 1 over 2. Then we'll have 1 here. Here we have 0, right? And multiplies by -1 and add this here, it will be 0. Multiply the last row by -2 and add here, it will be 0. In similar way, multiply, all right. So one more 0. All right, so that is, here we have 1, 1, 0, 0, 1, and here we have 0, 1, 0, 0, 1. Immediately, if I multiply by -1 and add to the first row, here we will have 0, here we will have 0. And the third one is 0 multiplies by -1 and add here, here we will have 0, here we have 0, here we have just 1, and here we have -1. And here we have 0, 0, 1, 0, 0. Okay. Now if I just interchange the third and fourth row, and we will get reduced row echelon form of this matrix. So here we have 1, 1, 2, 3, 4, 0, 1, 0, 0, 1. Here we have 0, 0, 1, 0, 0. And here we have 0, 0, 0, 1, -1. Right? Now it is in reduced row echelon form. These are leading entries. So from here, the first one, what is it? A. A equals 0. Second one,